Thank you very much. Thank you to the organizers, Alejandro, Tom, and Lauren, for inviting me. It's a great honor to participate in this event, which honors one of the truly outstanding mathematicians that I've known in my lifetime. So I've chosen a talk that I hope will intersect with a lot of things that have been interesting to Richard Stanley over the years. So here we are. Here's the birthday boy, his desk. The talk itself will focus on someone who has been important to both Richard and to me, namely Percy Alexander MacMahon, who died in the early 1930s and whose work in combinatory analysis spanned a number of decades in the early part of the century. So at a recent conference honoring Bruce Sagan, Richard gave a wonderful talk starting with the theorem independently discovered by MacMahon and Schmidt. The theorem is this: the number f of n of partitions of n, which no part appears exactly once, equals the number of partitions of n into parts not congruent to plus or minus mod 6. So here is an example of the things with non-singletons. There are 6 such partitions of A, and the partitions in which there are no parts congruent to 1 or 5 mod 6 are listed in the second row. There are also 6 such partitions. This reminded me that I published a short paper, I think it was in 1966, so that's a typo. So it's old paper is and old I am. Generalization of the partition theorem of MacMahon, which was based on the same result of MacMahon that Richard was citing, and that's what formed the idea for this talk. MacMahon was a pioneer in combinatorics and wrote a 2-volume work, Combinatory Analysis, which was the go-to book combinatorics for almost half a century. Today, Richard is clearly the preeminent combinatorialist, and his 2-volume work, Enumerative Combinatorics, will surely be the go-to book in combinatorics for much more than half a century. Richard perhaps best described MacMahon's importance as follows. So I'm quoting Richard now. Before 1960, there were just a handful of mathematicians who did a substantial amount of enumerative combinatorics. The most important and influential of these is Percy Alexander MacMahon. He was a highly original pioneer whose work was not properly appreciated during his lifetime, except for his contributions to invariant theory and integer partitions. Much of the work in enumerative algebraic combinatorics in the 60s and 70s can trace its roots in things. Some salient examples are his anticipation of the theory of p-partitions, his development of the theory of plane partitions, his work on permutation and integration. It's also interesting that he gave the Rogers-Ramanujan identities a combinatorial interpretation. So how did someone like me, who considered himself a number theorist, actually a student of Hans Rademacher, wind up in the world of P.A. MacMahon? There's the answer. Giancarlo Rota, who was Richard's thesis advisor, and who is a man who infinitely helped me in my early career, to whom I am deeply and eternally indebted. I spent my sabbatical at MIT in 1970-71 as a visiting professor. Rota's seminar was in full swing, and regular attendees included Richard, Dennis White, Curtis Green. In addition, there were many visitors, so it's a lively and active group. And in the middle of the year, Rota invited me to edit a collected papers of MacMahon for the MIT Press. This is a good idea. First thought was, MacMahon's been dead for 40 years. Surely this work was out of date. My second and much better thought was, what a great way to learn the mathematics influenced by MacMahon. I will write to everyone who has cited MacMahon for advice and comment. This provided the substance of the commentary I provided for the collected works. So I wrote to many people. Here's a letter from Richard Stanley himself after I sent him the published first volume. Here is a page letter from Martin Gardner, basically promising one of his columns in the Scientific American to be devoted to something related to MacMahon and advertising the appearance of the collected works. Basically, it was a truly fascinating article on what we called MacMahon's 30 colored cubes. Here is a letter from one man in the front row, Don Knuth, who was very helpful in this project as well. This is Giancarlo wrote his handwriting, which is the preface, the first page of the preface to the volume 2 of the collected works. He wrote prefaces for books. Here's one of the most interesting things that I received. MacMahon, in addition to being a combinatorialist, also was at one time in his life president of the Royal Astronomical Society. And he'd actually written one paper on basically studying the stars under the conditions of a total eclipse. This appeared almost immediately after Arthur Eddington, the famous British physicist, much more known in physics and astronomy, that MacMahon published an article crashing MacMahon's paper. However, the telescopes at the time were inadequate to determine who was actually correct. But as Edward Mather notes in this article, MacMahon was correct almost into the last detail, and it is surprising that Eddington would proceed in such a shoddy way to write something that was so far wrong. But this was, MacMahon was confirmed in his astronomy many years after his death. So I really want to spend my time on two topics in MacMahon's work that have interested me most. The partition analysis that I'm talking about is very definitely related to much of the work in Richard's PhD thesis, although, as he notes in the introduction, MacMahon's interests were in a very different direction from those that Richard pursued in his thesis. And so this would be more in the direction that MacMahon was interested in. Indeed, MacMahon's object in developing this topic was to prove his conjectures, the theory of plane partitions. But after about 100 in his combinatory analysis, after about 100 pages of developing this theory, he then tells us that he's unable to prove his conjectures using this work. So, not surprisingly, it took a long time before someone as brilliant as Richard realized that there was something of real value here. And I'm going to follow this up in a direction more like what MacMahon was interested in than what Richard was. So this is the idea. You're looking at multiple Laurent series, and you have this operator, omega, with the greater than or equal sign below it. Basically, what it does is to look at such a series, it cancels out any term that has a negative exponent on any of the lambdas, and for all the other terms, it sets lambda 1. And this provides a way of coding various partitions with various differencing conditions on parts, as you will see fairly shortly. There are a variety of very elementary formulas that can be used in an algorithmic setting to prove some rather startling results. And here is an example. If you apply the omega operator to the expression you see here on the screen, the result is the right-hand side, and the proof is quite easy. You expand both the expressions you see on the left in a geometric series so that you see the powers on lambda, and now you determine only those terms where lambda has a non-negative exponent, and that appears this line right here. And now you sum everything up using the geometric series. Again, you wind up with the thing at the bottom of the screen. There are, as I say, numerous formulas like this, and here are 3 of them that are proved in exactly the same way that you saw the example of the previous slide. since 1998, there's been a continuing series of papers, almost all of them joined Pella, under the title MacMahon's Partition Analysis. There are 15 titles related to this picture. Many of them deal with partitions on particular graphs. So here is one example. We have this set of diamonds hooked up at these vertices, and the inequalities in between the parts are indicated as you see up on the screen. And usually using partition analysis, it's not difficult to show that this is the generating function, and the coefficients 7 and q to the 4th. Here are the 7 partitions that arise in the setting. This is not really a thrilling result because if the generating, well, it's, I suppose when you're sitting at the computer working, you first see a sort of a thrill, but after that it loses a little something because this is not a modular form, so that you cannot expect that there will be, excuse me, serious arithmetic consequences resulting from this. So now I want to turn to something where I will apply partition analysis to a problem that was in the American Math Monthly in 1999. Frank Schmidt posed the following problem. So the P of n is the total number of partitions of n. Let f of n denote the number of partitions with distinct parts. Partitions of any number whatsoever with distinct parts where the first, third, fifth, seventh, etc., the odd indexed parts add up to n, and then his claim is that P of n and f of n are the same. So here, for example, are the 11 partitions of 6, and below you see the 11 partitions of distinct parts, where the first, third, and fifth part always add up to 6. The solution published was by Peter Mork. The Monthly also noted 8 others that solved the problem. And Mork's solution is indeed clever, marvelously clever. He takes the Ferrer's graph related to the partitions. This is the idea is 7, 4, 4, 3, 1. Here's the Ferrer's graph, 7, 4, 4, 3, 1. And he marks the nodes on the main diagonal and the diagonal above the main diagonal, and then he now computes the hooks at the squares marked x, and so you can see that there are 11 squares in this hook and 9 squares in this, and so on. And this is a bijection between the ordinary partitions and these partitions into distinct parts where you only pick up the first, third, fifth, etc. Why is that true? Look, the only, if you look at this, will be the hook for the first, this is the hook for the third, this is the hook for the fifth. It's clear that the content of those hooks consists of everything in Ferrer's graph, so that necessarily knows that just by this construction, first, third, and fifth entries in this are going to add up to the same thing as the original partition. So it is possible this. So is there an easy way to see this as bijection? The answer yes, it is. Pass before your eyes at a very rapid rate. Oh, it's going to see rapid rate. Anyway. I don't have time really to go through it all, but basically you start with the lowest square and hook them on reverse order to get to the top, and so you wind up with the original partition. So it's a very straightforward and lovely construction. The only problem with it is it's very hard to see if there's any way that it generalizes to anything. It's one of these sort of combinatorial gems that seems unrelated to anything else. But there is a much more prosaic way to achieve this. And that is as follows. Namely, if I want to look at partitions with distinct parts and I want to keep track of the first, second, third, fourth, fifth, in other words, instead of just having a general variable Q, I have as many variables as necessary, x1, x2 up to xn, where the exponent on x1 is the largest part, x2 is the next largest part, etc. Then how do I code that using partition analysis? And the answer is the way that you make the first part larger than the second part is to have a lambda put in with this exponent so that the omega operator will annihilate that unless J1 is greater than J2, similarly J2 greater than J3, etc. So if you have n summands where the last one is greater than or equal to 0 and they are distinct, then using the formulas that I showed you early on, they click in one after the other and produce a easily established that this is the relevant generating function. So how does that relate to Morg's problem? Well, the point is, in order to look at the first, third, fifth, seventh summands, all you need to do is set x1, x3, x5, x7, etc. equal to q, and the given index x is equal to 1. And this, since we were dealing with distinct parts where the last one was greater than or equal to 0, we're dealing with summands where there are either 2k or 2k minus 1 parts. So the result of that substitution into this expression is this, and this is a very familiar form. It appears in an identity that is often attributed to Euler. And of course, Euler's collected works stretch out farther than this, so I don't know that anyone has tracked it down for sure, but at least in the obvious places to look at Euler, this formula does not appear. It appears in a natural way in the work of Jacobi because in proving the Jacobi's triple product identity, this naturally rose as something he needed to prove. So anyway, I've attributed this to Jacobi, and so there the identity is. Of course, this has none of the glitter or sparkle that Morg's solution had, which, as I say, was extremely clever. But since it effectively algorithmic, you can apply it to almost any other circumstance you want. In particular, here there should be 3 dots out here missing. In particular, if I return to this situation of the old days with transparencies. Flicking through thousands of pages. Anyway, now instead of adding up all the summands, we just add them up those, and the generating function in this case turns out to be this expression, which is effectively a modular form, and thus there are very interesting and nice arithmetic properties of the coefficients of the power series expansion of this product. So my final topic of this morning arises from MacMahon's paper, Divisors of Numbers and the Continuation of the Theory of Partitions. MacMahon's combinatory analysis appeared in its 2-volume work, appeared in 1915 and 1916. And so not too much attention is paid to what he wrote afterwards, but he wrote mathematics for another 10 years at least. And in the early 1920s, he wrote a couple of papers on generalizing the idea of divisor sums to the theory of partitions. So MacMahon's starting point is the observation that the number of divisors of n is the number of partitions of n into parts of only one size. So the divisors of 6 are listed here, and the 4 partitions of only one size are listed below, and it's obvious what the relationship is because, as we learned in elementary school, addition is multiplication is successive addition. The relevant generating function for the number of divisors again is clearly the series. You can easily see that expanding the denominator in this sum end into the series. In addition, the sum of the divisors been denoted by sigma 1 of n is of interest, and the generating function is, as we see here. A1 of q is especially interesting because it's equal to this form for E2, where E2 is, I would say, the fundamental quasi-modular form. So let me give you a one-page refresher course on quasi-modular forms. So basically, you're looking at these divisor sums raised to powers. So sigma sum m is the sum of the mth powers of the divisors n. And basically, the E functions are defined in the way that you see here, except that this should be, this is multiplication, it's not addition. Sorry about that. And the range, so why are they called quasi-modular forms? It's because the E2 transforms under the modular group almost like a modular form. There's a constant term that gets thrown in that is extraneous that wrecks it as a modular form, but it is so close to being a modular form that they chose the not sounding really very happy quasi-modular form for these sorts of functions. MacMahon now considers what happens when we consider partitions of n with exactly k different part sizes. So if we have one part size, that's the number of divisors of n. So this is how he is going to consider the generalization. The divisors, and the generalization for the sum of the divisors will be exactly what you would expect when k is equal to 1. This is then the generating function for the sum of divisors. MacMahon later asserts in his paper that these AKs, which are the coefficients of this line series, unfortunately, is expressible as a linear function of the sum of the uneven powers of slices n. In other words, he basically asserted that it is a quasi-modular form. And he goes on to prove that that's true in the cases n equal 2, 3, and 4. Of course, n equal 1 is the quintessential quasi-modular form. So in 2013, Simon Rose and I proved MacMahon's conjecture. And it basically involves an argument that would have pleased MacMahon. You'd start out with a function where I'll justify this in a moment. It's basically the Chebyshev polynomial, and odd subscripted, evaluated x over 2, and you're summing over this q to this standard quadratic expression that one sees in classical theta functions. And then the theorem is that this f of x is actually the generating function modulo of product for these AKs, these coefficients in the these generating functions for the generalization of divisor sums. And a corollary is once you have this formula, is you use the standard expressions for Chebyshev polynomials to deduce precisely a generating function that looks now very much like a derivative of a classical theta function. And indeed, that effectively is what it turns out to be. And you find a recursion relation for the AKs in terms of previous A's and derivatives of previous A's. And this basically is adequate to show that these are in the ring of quasi-modular forms. Proof of the theorem, well, proof of the theorem goes as follows, namely, The Chebyshev polynomial tells us that this is actually cosine of 2n plus 1 theta. You now write down what this is. You change it into the bilaterally infinite series, and this then sums up to a product by the Jacobian product identity. And we now work back to get things involved with x, where x was 2 cosine theta. And finally, last line, pick out the coefficient of x to the odd power. Natural expansion of the set of the product tells you that it is these divisor sums. So there is a lot of arithmetic interest in these coefficients, which Rose was interested in certain algebraic geometry applications and not in this particular theorem itself. But there are numerous arithmetic results. I'm listing a few, just a few here. For example, that this MO of K, MO of 2n is congruent to 0.3 whenever 3 does not divide n. This is not too difficult to work out because if you take the formula that you have for this mod 3, the infinite product front collapses to a function of q cubed. So you only need to look at whether or not you get anything, whether or not everything else is divisible by 3 when you have an exponent that's not divisible by 3, and you find out very quickly that you have the case of 3n plus 2 and 3n plus 1. Both of these are congruent to 0.3 because either the term is missing, as you see here, or if you can force the exponent to be 1 or 2, not 3, then it turns out that the expression coefficient of that power is divisible by 3. So there are numerous things that go on with this. At the end of our paper, we conjectured this. This is subsequently by Singh. In addition to this, Ono and 2 colleagues have now utilized this MO function to be a prime identifying function. In other words, there's certain linear combinations of these partition functions, which anytime they are positive, they have to be prime. So this is similar to Maciejewicz work in the 60s, where showing that there were certain polynomials which, well, they're variable polynomials, which they're only positive, only 2 positive numbers. So it's really, this is now reaching other things. Finally, I want to say that instead of just looking at the case where alpha is -2, which is what we've been looking at before, when alpha is 0 plus or minus 1 or plus or minus 2, these series are very interesting because, in effect, they also fall into quasi-modular forms. And one of the most appealing examples to give you some idea of this is that when alpha is 1, you have this series. It is mod 3. This series is congruent to the series involving MO, A2 series. But in this case, the coefficients of 3n plus 1 and 3n plus 2 are not only congruent to 0.3, as you can see from this, they are actually 0. There are no coefficients that are powers of q that are not divisible by 3. And of course, this is the generating function. So these are the sorts of nice things that follow in this project setting. Here is a list of a few references. say thank you and happy birthday.